जी, अस्सलाम वालेकुम डॉक्टर अजमल।
Walaikum salam. Can you hear me?
हाँ जी, I can hear you. Thank you so much for connecting.
Thank you.
Would you like me to proceed with the introduction?
Yes, of course.
Thank you. Thank you, audience. I'd like to introduce Dr. Muhammad Ajmal, who's currently Assistant Professor of Chemistry at the Department of Chemistry, Division of Science and Technology, University of Education, Lahore. Dr. Ajmal received PhD degree from Quaid-e-Azam University, Islamabad. His primary research area is the synthesis of polymer hydrogels and the fabrication of metal nanoparticles, metal oxide nanoparticles, quantum dots, and carbon dots in the hydrogels for their applications in absorption, catalysis, and sensing. He's also worked at the Nanoscience and Nanotechnology Research and Application Center, COMU, Turkey, on a very prestigious fellowship. Dr. Ajmal has published approximately 41 research articles in international journals of impact factor with an accumulative impact factor of 165. He has presented his research work in many international conferences in Pakistan and abroad also. I'd like to welcome Dr. Ajmal to start his lecture. Thank you very much, sir.
Very for your kind introduction. Let me first share the presentation over here.
Thank you. Ji, assalamu alaikum, sir. Is it connecting?
Right.
Maybe there is connectivity error at his side.
Ji, Dr. Saab, can you connect again?
Hello.
Hello, जी, Assalamualaikum, Dr. Saab.
वालेकुम सलाम, आपको मेरी आवाज आ रही है?
हाँ जी, अब आ रही है. I think there was a connectivity issue.
ओके,
जी.
स्क्रीन शेयर हो रही है?
नहीं जी, अभी नहीं हो रही, लेकिन if you have opted तो वो I think थोड़ा lag है, but otherwise inshallah I think it will be uploaded.
मैं ये शेयर कर रहा हूँ, काइंडली ये मुझे कंफर्म कीजिएगा. आपका माइक ऑफ होता है तो वो फिर जब मैं बोलता हूँ तो समझ नहीं आती मुझे.
हाँ जी,
देखिए.
अब we can see the screen. जी.
ओके. अगर
जी जी
दरमियान में कोई इशू होता है तो काइंडली मुझे उस वक्त
जी
इन्फॉर्म
जी
कर
जी
दीजिएगा.
जी जरूर. थैंक यू.
ओके. थैंक यू वेरी मच. सो आई कैन स्टार्ट नाउ.
जी जी बिल्कुल.
So the topic of my today's talk is stimuli responsive hydrogels as versatile adsorbents and templates for the controlled fabrication of nanomaterials with tunable catalytic and optical properties. This topic has been demonstrated in this figure that these hydrogels can be used as adsorbents for the decontamination. For example, for the decontamination of water, that when it's added into contaminated water, then the contaminations are encapsulated by the hydrogels, and then hydrogels can be removed out from the water along with the contamination. So in this way, they can be used as adsorbents. These hydrogels are actually materials which can swell and deswell in specific solvents, as shown in this diagram. When they will deswell, their size is decreased, and when they swell in any suitable medium, then their size is enhanced. These hydrogels can be used in nanotechnology for the preparation of different nanomaterials. For example, the metal nanoparticles can be prepared inside these hydrogel networks. And once these hydrogel networks, sorry for the interruption. Once these hydrogel networks contain the metal nanoparticles, then these metal nanoparticle containing hydrogels can be used again as adsorbents. They can also be used as catalysts for different reaction mediums. And they can also be used for as a sensor, and this sensing can be temperature sensing, or it can be pH sensing, or it can be glucose sensing, or it can be ionic concentration sensing, as shown in this diagram, that this sensing can appear in the form of shifting in the optical response of these metal nanoparticles. And these optical properties and catalytic properties can also be controlled by applying the swelling and deswelling stimuli for the hydrogels. If we talk about the importance of the hydrogels, then these hydrogels have found applications in different fields. For example, they are being used in drug delivery. They are also being used in transdermal drug delivery. They are being used in contact lenses, and silicone contact lenses or silicone hydrogel contact lenses are also available in the market now. The wound dressings are also being prepared with hydrogels, and hydrogel wound dressings are also available in the market. And similarly, hydrogels are also being used in the tissue engineering, disposable diapers, and they are also being used in the agriculture as well. These are different fields where hydrogels have been transformed from a laboratory into the market. But the most emerging area of the hydrogel is they're used in the nanotechnology, specifically in catalysis and in sensing applications. If we talk about the importance of the hydrogels with respect to the economy of the country, then here is a display are the expectations from the US people that hydrogels, the market, our hydrogels market is increasing day by day. And currently, hydrogel products are 23.78 billion US dollars, and it's expected that this market will also increase within 10 years or within 8 years to $37.98 billion. And if we talk about the research or academia or the interest of the academia into the hydrogels, then it can be seen from this graph that since the discovery of the hydrogels in 1960, where for the first time synthetic hydrogels were prepared, research, although it was very slow in the initial stages up to 1985 or 1990, but later on, it has exponentially increased, and the number of research publications have increased over 100,000 articles in 2022. So this shows that how hydrogels are important, both for academia and industry from their application point of view and from their research point of view. Now, if we talk about the introduction of the hydrogel or the basic concept of the hydrogel, that what the hydrogels are, then these hydrogels are actually three-dimensional polymeric networks which exhibit the ability to swell and retain a significant amount of water within its structure, but does not dissolve in water. It means that it can swell and deswell in water, but upon swelling and deswelling, its structure is not broken down in water. These hydrogels can respond to various external stimuli, and due to this response, these hydrogels are also known as intelligent hydrogels. For example, they can respond to external stimuli, pH. They can also respond to temperature. They can respond to electric field and magnetic fields. They can also respond to ionic strength, and as well as to the glucose concentration of the external medium. And this response of the hydrogels to these external stimuli appears in the form of swelling and deswelling. Whenever any of these external stimuli is applied, then this hydrogel undergo swelling or deswelling. It depends upon the chemical nature of the hydrogel, that to which external stimuli it responds and how will it respond. I will also talk about this response in upcoming slides. For example, here is the pH responsive hydrogels. The hydrogels containing acidic or basic functional group can respond to pH of the external medium. For example, if we have a hydrogel containing the carboxylic groups, that will be acidic in nature, then at low pH value, the size of the hydrogel piece of the hydrogel particle will be smaller, and the smaller size is due to the protonation of the acidic functional groups. But as we increase pH of the medium, this increase in pH of the medium results in the deprotonation of acidic functional groups on the hydrogels, and negative charges are created if the carboxylic groups are present in the structure of the hydrogel. These negative charges will repel each other, and this will result in the extension of the polymer chains. When the polymer chains will be extended within the hydrogel network, then size of the hydrogel network is increased, which can be seen in this figure, that if we have any anionic hydrogel or an acidic hydrogel, then at higher pH value, when the acidic groups are deprotonated, then size of the part or a piece of the hydrogel or a particle of hydrogel is increased. Similarly, if we have a basic hydrogel or a cationic hydrogel, then a reverse trend will be observed, and the same chemistry is involved over here as well. Another example of the external stimuli or the stimuli responsive hydrogel is temperature responsive hydrogels. When temperature of the external medium is changed, the size of the hydrogel particles is also changed. For example, if we have a hydrogel containing N-isopropyl acrylamide in its structure, then this component has a hydrophobic and hydrophilic functionalities in itself. For example, the backbone and the isopropyl group are hydrophobic, while the amide group in this N-isopropyl acrylamide is hydrophilic. At the lower temperature, these hydrophobic groups dominate over the hydrophilic group. The hydrophilic group dominate over the hydrophobic groups, and therefore at lower temperature, particle size of the hydrogel particles is larger. However, when the temperature is increased, particle size decreases due to the breaking down of the hydrogen bonding between amide groups and water molecules. And these hydrogen, with the breakdown of the hydrogen bonding, water molecules are expelled out from the hydrogel network, and the polymer chains are shrunken. And at the same time, these hydrophobic groups dominate over the hydrophilic groups, and the size of the particle, hydrogel particle, is decreased. These hydrogels can be classified into different classes based upon different parameters. For example, based upon the source, these hydrogels can be classified into natural hydrogels or into synthetic hydrogels. And similarly, based upon the composition, these hydrogels can be classified into homopolymer hydrogels and copolymer hydrogels. And as expected, natural hydrogels have been gradually replaced by synthetic types due to their higher water absorption capacity, long service life, and wide varieties of raw chemical resources. So I will further talk about the synthetic hydrogels which are being prepared in the laboratory nowadays. These hydrogels can also be used as reactors for the synthesis of metal nanoparticles. So this is how the hydrogels are being transformed or are being used into the nanotechnology. And once a hydrogel network is prepared, it's a very simple approach for the preparation of metal nanoparticles with the controlled size, that by controlling this mesh size, which can be controlled by controlling the cross-linking density and by controlling the concentration of monomers, which have different functional groups and which can absorb the precursor of the metal nanoparticles. For example, when metal ions are metal ions can be loaded into the hydrogel networks, as shown in this figure, that in the first step, these hydrogels can be loaded. Metal ions can be loaded into the hydrogel network. And in the second step, those metal ions can be reduced by using a suitable reducing agent, and that reduction of the metal ions result in the formation of metal nanoparticles, and then this hydrogel is converted into a composite or into a hybrid system which contains the polymeric network as well as the metallic or the nanometallic part as well. So what are the advantages of using the hydrogels as reactors for the preparation of metal nanoparticles? If we use the hydrogel networks as reactors for the synthesis of metal nanoparticles, then these hydrogels can not only act as the reactor medium in which the metal nanoparticles can be prepared, but they can also act both as chelating agent and capping agents for the stability of metal nanoparticles. So there is no need to add any additional capping agent for the stabilization of the metal nanoparticles. So the metal nanoparticles are also protected from the atmosphere, hindering the oxidation or deactivation and aggregation, so allowing the increase in their stability and longevity. So this is how the hydrogels can be used as an advantageous material for the synthesis of nanoparticles. And the hydrogel-supported metal nanoparticles can be successfully used as the catalysts and as sensors in different mediums without any further modification. So here is an approach that how can we control the morphology and the size of the hydrogel or the size of the nanomaterials which are being prepared inside the hydrogel network. For example, the first approach is the cross-linking density. If we can control the cross-linking density or we can tune the cross-linking density, then we can also tune the particle size as well. As shown in this diagram, in the first figure, we have lower cross-linking density, therefore we have large mesh size. And in the large mesh size, where this mesh size can accommodate large number of metal precursors, which are metal ions, and when they will result, they will be reduced and aggregated with each other to form a metal nanoparticle, then that particle will be of greater size as shown in this figure. So if we decrease the cross-linking density, then the capacity of each mesh to accommodate or to absorb the precursors of metal ion will decrease, and that will result in the formation of smaller metal nanoparticle upon the reduction, and similarly the particle size can be further reduced as well. Second is the metal ion binding groups. If we use different functional groups in the polymeric hydrogels and we don't change the cross-linking density, then again we can control the particle size of the metal nanoparticles, because different functional groups have different binding ability towards different metal ions. So by variation in the functional groups which are responsible for the absorption of metal ions in the hydrogen structure, the particle size of the metal nanoparticles can also be controlled. And finally, the metal precursor field is also an important parameter, that if we have smaller field, a lower field, then each mesh will have lower amount of the precursors, and it will result in a smaller, relatively smaller metal nanoparticle. And if we increase the field of the precursors, then each mesh will have larger amount of the metal precursors, and that will result in the formation of a larger size particles. Now, I will discuss a few research articles which I have published in this field by using the hydrogels, where hydrogels have been synthesized and used for the synthesis of metal nanoparticles. For example, here is the first one where we have prepared polymethacrylic acid hydrogels in the form of micron-sized microgel particles. And this synthesis was carried out with inverse suspension polymerization method at just 40 degrees centigrade. And once these hydrogels were prepared, it was observed that they were having almost spherical morphology, and their particle size was around 200 micrometers. Most of the particles were having size around 200 micrometers. So these hydrogels were used as reactors for the synthesis of copper, cobalt, and nickel nanoparticles. In the first step, the precursors of these metal nanoparticles, which are of course their metal ions, they were loaded in the hydrogel networks. Methacrylic acid contained the carboxylic group. This carboxylic group was first deprotonated by treating with a base, and then it was used or exposed to the copper ions, cobalt ions, and nickel ions. And the absorption of nickel ions, cobalt ions, and copper ions can be seen from the change in the color of the hydrogel. That as the metal ions were loaded in the hydrogel networks, the color of the metal ions was imported on the hydrogel. And when these metal ions were reduced by using sodium borohydride as a reducing agent, then they were converted into the metal nanoparticle, and the appearance of the black color in the hydrogen network was an indication of the formation of metal nanoparticle inside the hydrogel network. However, the formation of the metal nanoparticle was further confirmed with transmission electron microscopy. And as it can be seen from these uh, and in case of software, and up to
Ji, Assalamu alaikum, Dr. Saab. I think we can't hear you.
Hello, Dr. Aisha, can you listen me?
Yes,
Ji
sir.
sir.
Okay. So here I was talking about the thermal stability. So these hydrogels are thermally stable below 200 degrees centigrade, and they can be used effectively for industrial application below this temperature. So here are some catalytic applications of these hydrogel systems. It's the catalytic potential of these composite hydrogel was investigated in the catalytic reduction of three different environmental water pollutants: 4-nitrophenol, 2-nitrophenol, and 4-nitroaniline. And these industrial pollutants were selected because their reduction is very, very slow or deadly slow in the absence of any catalyst. And as it can be seen from this first figure, that in the absence of a catalyst, when only sodium borohydride was used, then even after 180 minutes, there was very small decrease in the concentration or in the absorbance of the reaction mixture, which is of course of the 4-nitrophenol, which is considered as a toxic water pollutant. However, when a small amount of a catalyst was used in the same reaction mixture, then the same amount of the 4-nitrophenol was degraded within just 120 seconds. So this is how these catalysts can be effectively used for the reduction of uh, water pollutants, and same was observed in two other water pollutants or nitro compounds, that in case of 2-nitrophenol, the 2-nitrophenol was degraded within just 90 seconds, and nitroaniline was also degraded within just 90 seconds. And here, here is the magnetic behavior of these composites containing cobalt nanoparticles. That when cobalt nanoparticles, which are magnetic in nature, are prepared in a hydrogel systems, then the overall cobalt hydrogel composite system becomes a magnetic system. And this magnetic property is provides an advantage to control the catalytic behavior or the catalytic property or the catalytic activity of the system by applying the external magnetic field during the reaction medium. As it can be seen from this figure, the magnetic properties can be observed from here, that when we applied an external magnet, all the composite particles are attracted towards this externally applied magnet. Here is the effect of different parameters, although it is related towards the kinetics of this catalytic reaction medium. So I will not go into the details because it seems beyond the scope of our today's talk, but just for the new learners, that when you have to apply kinetics, then first of all, you need to verify that which kinetic model can be applied on your system. So this is how we have investigated first the concentration of the reducing agent, and we have found that when the concentration of the reducing agent increased from the 50 times, then the concentration of reducing agent was having no effect on the catalytic rate of the catalytic reaction. So all the reactions were carried out by using the concentration of reducing agent of 50 times higher as compared to the reactant. So the effect of change in concentration of the reducing agent was not considered, and pseudo first order kinetics was applied, and it was observed that in case of all the composites containing nickel, copper, and cobalt nanoparticles, we have obtained significant catalytic activity. And this system was also temperature responsive up to some extent, and by increasing the temperature of the reaction medium, the catalytic activity of the system was also increased, or rate of the reaction was also increased. And similarly, we have calculated some thermodynamic parameters just by applying the Arrhenius equation and our Eyring equations, because whenever we are going to observe a reaction, then these thermodynamic parameters are also very important, that what is the kinetic activation energy and enthalpy change during this reaction, and entropy change during this reaction. This negative value of the entropy change shows that the formation of the activated complex was a favorable process, because the entropy of the system was decreasing, which shows that disorderness was decreasing. It means that the reactants were combining with each other, and disorderness was decreasing in the reaction mixture. And it shows the good catalytic activity of a system, because whenever we have a good catalyst, then the reactants should easily adsorb on the on the surface of the catalyst. And when they are adsorbed on the surface of the catalyst, then disorderness decreased and orderness is increased. Catalytic potential was also observed for some other water pollutants, which are dyes, and we have considered both the cationic and anionic dyes. Here is the catalytic reduction of eosine Y and methyl orange, and then it was also observed that this catalyst can also act as a catalyst simultaneously if we have multiple pollutants in the same, or if we have multiple reactants in the same reaction medium. So by using this catalyst, we can degrade multiple water pollutants present in the same reaction mixture. So here is the mechanism of a catalytic reaction. That first of all, in general, if we see the catalytic reaction, then this is the reactant, which is converted into the product in the presence of this catalyst, and sodium borohydride will be present in the reaction medium as a reducing agent, and water is the solvent of the reaction. Then how this reaction takes place? Actually, initially at the first, this borohydride and the reactant, which is nitrophenol, both these reactants are adsorbed at the surface of the catalyst, as shown in this diagram. That first borohydride is being adsorbed on the surface of the catalyst, and then adsorption of the nitrophenol takes place on the surface of the catalyst, and then stepwise reduction of the nitrophenol occurs, and finally when the product is formed, that product is desorbed, and this catalyst becomes available for its catalytic role again, and the same cycle is repeated again and again in the reaction medium. And another advantage of using the hydrogels or microgels in catalysis is that the nanoparticles, which are currently considered as very effective or efficient catalysts in many reactions, but they have a disadvantage that when the reaction is completed, then due to their very, very small size, it becomes very difficult to separate these catalysts from the reaction medium so that the product can be separated out in its purified form. However, if you have only nanoparticles, then you need to use expensive techniques like high-speed centrifugation or very high, which becomes very costly as well. However, when you use hydrogels or microgels, as we have used in our this system, then the nanoparticles are encapsulated inside a microgel particle. A microgel particle may contain 10, 20, or it may contain even 100 nanoparticles, depending upon its size. So due to larger size of the microgel particle, these nanocatalysts can be easily recycled by a simple process of the filtration, as shown in this figure, that when the reaction is completed, you can just filter the catalysts. The product will be passed out through the filter paper, and the catalyst can be recycled. And this recycling can be carried out by just simple washing with the solvent or with water, and then the same catalyst can be reused for its catalytic role in the next reaction. Another important feature of the catalyst is its reusability, that for how many cycles you can reuse a catalyst. Greater is the number of recycle, greater is considered as the effectiveness or efficiency of that catalyst. In this study, it was observed that in case of copper and in case of even cobalt, the catalytic activity was observed up to 4 cycles. However, in case of copper, a very small decrease of just 10% was observed in the catalytic activity, even in the 4th cycle. And in case of cobalt, A gradual decrease in the catalytic activity was observed. However, after fourth cycle, we were unable to recycle the catalyst because our composite was broken down in the system. So this was the point where we had to think that how can we improve this mechanical strength of our catalyst so that it can be reused for many cycles. We had to change the morphology of our hydrogel system. So this is very important point for the new learners, that how can you define your destinations in research? How can you define the innovations? And how can you find the research gaps? This was the point where we thought that we need to increase the recycling of our catalyst. And then there were various options that either we can change the metal salts, we can change the stabilizers, we can change the reducing agents. So among these from these various options, we selected one of these, that we should co-polymerize methacrylic acid with another system, because the literature says that if we have amido oximes in a polymeric network, then it can bind the metal nanoparticles strongly with it, and mechanical stability of the system is increased. So this was our target, and the amido oximes cannot be directly attached with the polymeric network. So first of all, we co-polymerized the methacrylic acid with the acrylonitrile. And then these nitrile groups were converted into the amido oxime groups. And again, we have found that these microgel particles were formed, and most of the particles were having particle size around 200 micrometer. And this conversion of the nitrile group into the amido oxime group was verified by using FTIR analysis, and it was observed that after the modification, the appearance of the nitrile functionality in the hydrogel was disappeared, and it was an indication that nitrile group has been converted into the amido oxime. And here is the pictorial and graphical representation of the this experimental setup, that in the first step, when we have prepared these hydrogels, which were of off-white colored, and they were modified nitriles into the amido oxime groups, and then they were used as reactors for the absorption of cobalt and copper metal ions, and very strong absorption of copper and cobalt was observed, as it can be seen from the intense colors of these metal ions. And then these metal ions were reduced into the metal nanoparticles, and it was also observed that the cobalt nanoparticles containing system was having inherently magnetic nature. And by applying an external magnetic field, these magnetic particles can be attracted towards that externally applied magnetic field. And in this case, we observed a very fine dispersion of the metal nanoparticles. They were well dispersed, almost homogeneous in size, almost homogeneous in shape. And this showed that how effective the amido oxime groups were for the synthesis of these metal nanoparticles. And we also observed strong catalytic activity, as it can be seen here. 4-nitrophenol and 2-nitrophenols can be reduced in the presence of these catalytic activity, in the presence of these catalysts. And there are different parameters which can be used to control the rate of the reaction. For example, we can change the amount of the catalyst, and by increasing the amount of catalyst, the rate of reaction is increased, which can be seen from this figure, that as the slope of these lines through the first order graph increased, the rate of the catalytic reaction is also increased. In this case, it was observed that by increasing the temperature, rate of the reaction was also increased, and it is also obvious that when temperature is increased, the average kinetic energy of the reactants is increased, and their effective collisions are also increased, and the formation of the rate of formation of the product is also increased. In this case, there was another interesting observation when we have used methylene blue as a pollutant. Uh, in case of methylene blue, we have observed that the catalytic action was very, very fast as compared to that in methyl orange and eosine white. This methyl orange and eosine white are negatively charged dyes, while methylene blue is positively charged dyes. In case of methylene blue, it was observed that due to the negative charge on the carboxylic groups of the microgel networks, these methylene groups have very strong rate of diffusion towards the hydrogel networks, and they are get absorbed on the hydrogel networks as shown in this figure, that when we add small amount of the catalyst in this system, then first these methylene blue molecules will get absorbed on the surface of or on the in the structure of the microgel networks. And as we added the reducing agent, the same methylene blue was reduced, and the black color of the catalyst was also reappeared in the final step. In this work, we have also demonstrated the simultaneous reduction of a nitro compound and a dye, and a nitro compound with a negatively charged dye, a nitro compound with a positively charged dye, and then positively and negatively charged dyes simultaneously, and then the three different pollutants. One is the positively charged dye, second is the negatively charged dye, and the third one was the nitro compound simultaneously. And it was observed that this catalyst has worked very well in all these cases as shown in this figure. First one, the 4-nitrophenol and eosine Y was degraded in this step, and both these reactants were degraded simultaneously. And second, 4-nitrophenol and methylene blue, this is positively charged dye, and methylene blue and eosine Y, this is positively and negatively charged dye. And then we have three different pollutants in the reaction medium, and all these three pollutants were reduced or degraded simultaneously with the help of these catalysts. And in this case, as I have stated earlier, that our target was to increase the recycling ability of the system. And we have observed that in this case, we were able to recycle the cobalt nanoparticle containing catalyst up to 5 cycles. And even there was no appearance of structural breakdown after 7th cycle, but due to time constraints, I can go only for until the 7th cycle, because every cycle almost takes 1.5 hours, because we have to complete the reaction, then you have to recycle the catalyst. After recycling the catalyst, you need to start the second reaction, and then it goes on again and again for the whole day. It was very interesting for us that in this case, of this catalyst are also having very good catalyst as well. Another important feature of the catalyst is its storage time or its shelf life. That after the how long
Ji, Assalamu alaikum, Dr. Saab. I think we've lost connection again. If you could double check your mic. Thank you. जी अस्सलाम वालेकुम डॉक्टर आरजू.
Walaikum Assalam. He has just reconnected.
हाँ जी, okay, great. जी अस्सलाम वालेकुम डॉक्टर साहब.
वालेकुम सलाम जी, मैंने दोबारा कनेक्ट किया है, आप सुन सकते हैं मुझे?
जी 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 बिल्कुल.
Okay.
Very interesting talk, Dr. Saab. Thank you for sharing this detailed lecture.
It's my pleasure. I think today's weather is disturbing the internet connectivity.
जी, no problem. Dr. Saab, you're also live, so which means के students या researchers they can connect with you via Facebook and YouTube live. So आपका lecture जो है वो वहाँ पे भी जो है वो चल रहा है live.
अच्छा, ये बता सकते हैं कि टाइम कितना है?
जैसे आपको मुनासिब लगे वैसे. It's been almost 1 hour, but we have मतलब I have a couple of questions, and Dr. Arzu is also connected via
Okay.
WEmpower Pakistan login.
Okay.
जी जी.
Okay, I will try to conclude this presentation within 10 to 15 minutes.
जी ठीक है जी.
Okay, I was talking about the adsorption capacity of the hydrogels, and these hydrogels can be used as adsorbents for the treatment, specifically for the treatment of contaminated water, which is also very important issue worldwide, because with the increase in the industrialization, drinking water is being contaminated day by day, and this contamination is increasing, and the treatment of this contaminated water is also very important. And although various treatment methods have been developed, but still search for the more economical method is in progress. And in this respect, the hydrogels are being considered as very interesting materials which can be used as adsorbents for the treatment of contaminated water. For example, in this present study, or in this study, which I am going to present over here, we have used this hydrogel system for the adsorption of 3 different types of pollutants. These are the heavy metal ions. These are the dyes. Among the heavy metal ions, we have studied chromium and cadmium. Among the dyes, we have studied rhodamine 6G and methylene blue, and a pesticide, which is paraquat. And it was observed that this system can adsorb all these type of pollutants from the contaminated water. However, as it is obvious that metal ions can form complexes with the change in pH of the medium. So it was observed that when we increase the pH, complexation of the metal ions was also observed. So below that pH, we have observed their adsorption, and it was observed that in case of cadmium, the maximum adsorption was at pH 6, and that of chromium was observed at pH 5. Above this pH, these metal ions were converted into the metal complexes, and they would get precipitated in the reaction medium. And their adsorption capacity was as high as more than 300 milligram per gram of the hydrogels for paraquat in this case. So this is the further modification of this hydrogel system, that we have used this hydrogel system for the synthesis of bimetallic magnetic nanoparticles by using cobalt and iron as the precursor metals, and we have prepared cobalt iron bimagnetic nanoparticle in this hydrogel system. And the indication of the formation of the hydrogel can also be observed without using any high resolution technique, that when we have pure hydrogel system, then it was all white, off-white colored, and when we have loaded a mixture of cobaltine and iron ions, then it was converted to the dark brown color, and when these metal ions were reduced into the metal nanoparticles, then jet black color was observed. And this STEM image again shows that this system was very effective for the preparation of well-dispersed, homogeneous in shape and size metal nanoparticle, bimetallic nanoparticles, sorry, in this case. And then these bimetallic nanoparticle containing the hydrogel system was also used as adsorbent. And it was used, and it was observed that this system retain its magnetic properties even when they are dispersed in the reaction medium, or even when they are present in the in water, or in the absence of water. No matter the hydrogel is in the form of dried form, is in the form of is in dried form, or it is suspended in any reaction mixture, it responds to the external stimuli. Now, what is the advantage of this magnetic field? I will discuss it in the next slide. Here, I will talk about this thermal stability, that this system was also observed to be thermally stable below 200 degrees centigrade. And it was uh, concluded from this observation that this system can be used at industrial scale for the treatment of contaminated water below 200 degrees centigrade. So here is the advantage of using magnetic behavior, or using the magnetic nanoparticle for the formation of these composites with hydrogels, that once the dye, or once a pollutant has been adsorbed on the hydrogel system, then you apply an external magnetic field. The adsorbent containing the contamination is attracted towards the externally applied magnetic field, and you can simply decontate the water which has been now purified. And another observation was also that when we increase, or when we have modified these hydrogel system with the fabrication of these metal nanoparticles, and their adsorption capacity was increased, this these first is representing that these graph bars are representing the adsorption capacity of my hydrogels containing nitrile groups. And it was observed that when nitrile groups are converted into the amidoxime groups, the adsorption capacity was increased. And when magnetic nanoparticles were prepared, adsorption capacity was again increased. An increase in the magnetic in the adsorption capacity, and an additional advantage of separation of the adsorbent from the reaction medium with the application of an external magnetic field was also observed in this case. So these were the advantages of using the hydrogel system of methacrylic acid, acrylonitrile, and its modification, and then using it as adsorbent and the fabrication of bimetallic magnetic nanoparticles. So this system was also used for the real applications in the double distilled water, in the tap water, for the river water, and even for the sea, from the sea water. That the contaminations were suspended, or were dissolved in the sea water, they were dissolved in the river water and in the tap water, and it was observed that the system was effective for all these mediums, although the activity or the adsorption capacity was decreased in case of river and sea waters. But this can be observed due to the presence of different metallic salts in the hydrogels, which in the sea and river, which can also be adsorbed on the in the hydrogel network, and they can occupy the adsorption active sites. This is another hydrogel system. In this case, we have prepared a zwitterionic hydrogel, which contain both the positive and negative charges on its structure. And again, we have prepared micron-sized hydrogel system, as it can be seen from this first figure, that almost all the particles were having size around 50 micrometer, and they are all in the same shape. So this is very important, that if you can prepare the hydrogels with the same morphology, then you can get good results in their applications. And in this case, we have prepared nickel nanoparticles, and very fine, well dispersed nickel nanoparticles were observed, as it can be seen from these two figures. And the thermal stability, the thermal analysis also shows the presence of nickel nanoparticles or the presence of some amount of the nickel in these structures, in these composites as well, and thermal stability of this system above 200 degrees centigrade. Again, the catalytic activity of the system was also very fine in the presence for the nitro compounds. And here is another polymeric system. I will go through it and move towards the, yes, here is the next improvement. In the previous studies, we have prepared our microgel systems in a temperature controlled assembly where the hydrogels were prepared in the presence of an inert atmosphere using nitrogen or argon. But after going through that those steps, now there was a stage we have thought that why not we should develop some alternate methods which can be cost effective, which can be time effective, and which should need low labor. And then we developed another strategy for the synthesis of hydrogel. Our target was that it should be easy synthesis. There should be no need of heating. There should be no need of steering. There should be no reaction assembly. So what to do? We have just to prepare our solution, mix up those solutions and prepare the hydrogels. Just by simple mixing, we have used an additional chemical that have acted as an initiator or boosted the initiator even at the room temperature. And this was a bulk polymerization. And in this bulk polymerization, we've just mixed the monomers in a simple beaker and initiator, and then an accelerator which initiates, which creates the which is responsible for the actually redox reaction and generates the free radicals even at low temperature, and the reaction can be carried out without any high temperature requirement, without any nitrogen atmosphere, and at low temperature we have prepared our hydrogel system. And that hydrogel system was also effectively used as a reactant for the synthesis of different metal nanoparticles, as in this case we have prepared copper and cobalt nanoparticles. So the swelling behavior of the hydrogel was also observed because this was a bulk hydrogel, and we have observed that when this hydrogel piece is added in, the dried hydrogel piece is added in water, it uptakes the water. When water uptakes occurs, the hydrogel piece is swollen and its size is increased, and percent swelling was observed more than 400 in this case. And even in this bulk hydrogel, when we have prepared cobalt nanoparticles, they have retained their magnetic characteristics even in these bulk hydrogel systems. And no matter those composites are present in dried form or they are suspended in a reaction medium. Here are the TEM images, and cobalt nanoparticles can be seen very easily in these TEM images, that very fine spherical in size cobalt nanoparticles of around 10 nanometer were prepared. In this system, thermal stability was again observed about 200 degrees centigrade. So this system can also be used at industrial scale. This was used as adsorbent as well as a catalyst for the reaction medium. These details I have already discussed. Again, the same parameters have been calculated. Recycling was also observed in this case. And interestingly, slight increase in the catalytic activity was observed after the first cycle when we studied the recycling. This increase in the catalytic activity of the first cycle can be observed due to the elimination of some impurities which can be adsorbed on the catalytically active sites during their synthesis. There might be some other reasons. For example, some catalytic sites can be masked during the first reaction medium, during the first reaction cycle, but when the catalyst is used for the first time in the reaction medium, its catalytic sites are exposed towards the reactant, and in the second cycle, those catalytic sites also become in excess for the reactants to get adsorbed over there, and so the catalytic activity was increased, and the same catalytic activity was observed till the fourth cycle, and no loss in the catalytic activity was observed. The adsorption capacity of the hydrogel was also remarkable, that we have observed more than 80% removal of malachite green in this case. The magnetic hydrogel system was also found to be very effective, and the adsorption capacity of the hydrogel was also increased by the fabrication of magnetic nanoparticles, with an additional advantage of removing the composite or removing this adsorbent by applying the external magnetic field. Now, I will talk about the chemical sensing or the optical properties of the metal nanoparticles. We have prepared nanogel system by a suspension polymerization, and after suspension polymerization, this was used for the synthesis of silver nanoparticles. And the STEM image shows the formation of silver nanoparticles. And once the nanoparticles were conformed in the hydrogel systems, these hydrogels were also found to be temperature sensitive, as shown in this figure, that we increased the temperature, size of the hydrogen particles was decreased. The chemistry of this process I have discussed earlier. And here is the optical properties of these noble metal nanoparticles, that when we prepare the noble metal nanoparticles such as silver and gold in the hydrogel networks, these nanoparticles show optical response, which means that when light falls on these systems, they give some response. And that response appears in the form of change in their lambda max, or in the form of change in their absorption intensity. For example, in this case, where this optical property is due to their surface plasmon resonance, which is the collective oscillation of the electrons present on the surface of the metal nanoparticles, that this collective oscillation or the surface plasmon resonance is the function of interparticle distance. This is the function of refractive index. This is also the function of shape and size of the nanoparticles. So as I have discussed in the previous slides, that we can control the shape or size of the nanoparticles just by controlling the mesh size. So if we have smaller mesh size, then we can prepare the particles with smaller size, and if we have smaller size, then they will have some different optical response as compared to those of larger size. And if we have prepared metal nanoparticles in a hydrogel system, then again the optical properties of that prepared system can also be tuned by just applying the external stimuli. In this way, that system can be used as a sensor system for the external stimuli, such as temperature, such as pH, glucose strength, and various other parameters. As we can see over here, that when this hydrogen system is in the form, is in swollen form, the interparticle distance is large, and when the same undergoes shrinking, then the interparticle distance is decreased. When the interparticle distance is decreased, then surface plasmon resonance effect is changed. This change appears in the form of change in absorption intensity, or in the form of change in lambda max, as it can be seen in this figure, that as we have changed the pH, or we have increased the pH, a red shift in the lambda max was observed. And it shows that this system can be used as a tunable optical system. And again, this system was also having catalytic activity, and this catalytic activity was observed in the reduction of 4-nitrophenol, and the formation or the synthesis or the existence of silver nanoparticles in another system was also confirmed, by this optical response, that when we have only hydrogel, there is no optical response. But when the silver nanoparticles are fabricated in the same hydrogel system, then the composite system gives an optical response. And it shows that the system can be used as an optical sensor because it has optical properties. And in this case, again, a red shift was observed when pH of the system was increased. And it shows that this system can be effectively used, or hydrogels can be effectively used for the synthesis of highly stable optical sensors. That stability can be observed from this figure, which shows that even after 40 days, the optical sensitivity of the system is not affected by the atmosphere. Similarly, here is again preparation of another thermoresponsive and pH responsive hydrogel, and then fabrication of the silver nanoparticles. And again, here is optical response of the composite, where there was no optical response of the pure gel. And then this system was also temperature and pH sensitive. And of course, the TEM image shown there the presence of silver nanoparticles, and here is the temperature and pH responsive of the hybrid systems as well, containing the metal nanoparticles. Here is again optical response, that how can we control the optical response when we change it from 2 to 10. Then lambda max has been shifted from 394 to 403. This change lambda max can be used as a tool for pH sensor of this system based upon optical response. Finally, we can conclude our this talk that hydrogels with different chemical compositions and morphologies can be prepared and used as reactors for the controlled synthesis of morphology, functional group, feed content of optical.
जी अस्सलाम वालेकुम डॉक्टर साहब। जी, I think we've lost connection again. Could you kindly reconnect for the Q&A session? Thank you.
Dr. Aisha, can you listen to me? I have reconnected again.
Dr. Sab, I can hear you now. Thank you.
Okay.
Thank you for sharing your lecture. I think it was very, very informative. In fact, indeed, the hydrogel system that you have described is a complete system. It has multitasking properties. So my background is peptide-based hydrogels for as biomaterials or as injectable materials. So my question to you would be, can we use these systems for biomedical applications?
Yes, I am currently working for the biomedical applications for drug delivery system. And I'm also collaborating with a research group in UK to develop some injectable hydrogel systems.
That's
Which
very interesting.
Drug delivery system. Yes.
So because my work basically revolves around using these injectable systems mostly for drug delivery applications. I've not actually moved towards biosensing at the moment, but I do know of this lady at NUST at ASAB who's working on biosensors and bioelectric applications of hydrogels and nanoparticles. So I'm really interested in fact, knowing more about your work. I will definitely go through your research papers because I feel that the biomedical aspect can be explored further. Also, I mean,
I have started antibacterial activity, and antibacterial applications have been reported in few articles in the last year. And the next task is the drug delivery, and my research students are currently working on this application, drug delivery applications of these hydrogels. So hopefully we will have some good piece of research in near future from the biomedical application point of view of these hydrogels.
this is great, G. Thank you so much. Another question that I have is that you mentioned these microgels. Can they be used as a separate system?
Separate system means separate from which?
So can they be used, for example, let's suppose if it's because you mentioned separation membranes. So I was interested if we had to kind of purify blood, let's suppose, which also consists of ions and radicals, etc. Can they be used for that kind of application?
Yes, although I have not done this work, but I have studied about the anisopropyl acrylamide, which I'm using in my research articles, that this is biocompatible and this can be used as the drug delivery system. And this can also, I hope that this can be used for the purification of the blood as well as the membrane. But I'm not exactly sure about that. I think I need to explore about this area.
Great, thank you. So I'm guessing that no animal work has yet been done using this system at the moment in
Yeah,
Pakistan or
yeah,
abroad.
I haven't done, but and as well, it has not been done in Pakistan. Some research group, as I have told you, I have just collaborated with a research group in Manchester, and they are doing work in collaboration with the hospital and with the pharmaceutical industry. So hopefully, we will have some good results in near future.
This is great. So University of Manchester, that's my alma mater. So where exactly? School of Materials or elsewhere?
Yeah. School of Materials. Actually, I am working with Tom McDonald. He was previously working at Department of Chemistry, Liverpool, and he has
Yes,
just,
yes, yes, yes. In
just
fact,
moved,
yes, I remember. I
yeah,
know
he
him well.
just moved to Manchester this month.
Okay, great. So he was in Liverpool. He was an assistant professor, I think, well, lecturer at Liverpool, and
Now
now
he is,
he's probably.
now he is a reader over there, chemistry.
Oh wow, this is great. Yes, he's doing a lot of great work. I think that's
Yeah,
a very good
very
collaboration to have.
applied, very applied work.
Yes, absolutely. So thank you so much, Dr. Saab. I think I will definitely connect you with another associate professor at NUST. I think she'd be happy to work with you.
Okay, I'm always happy to make some collaborations, and I would be ready to do any collaborative work.
Thank you so much, Dr. Saab, for your time, for your valuable time, in fact, and sharing your research work and your experiences with us. Thank you so much for today.
Okay, thank you very much for you. Thank you very much to you, and it was also a great forum for me to share my research work, because all these experiences always give some learning points as well.
Definitely. And I think it's mostly important for networking and finding great collaborators to work with, because as we
May I
all
know?
know, nowadays we can't really work alone. We have to have a very good network.
Good.
So inshallah, we'll definitely be in touch with you.
Yeah. May I know about your institution, because I'm not.
I finished my PhD 12 years ago from the University of Manchester. Then I've been actually working in China as a postdoc at Peking and University and the Chinese Academy of Sciences. Now I've come back to Pakistan. I'm working as associate professor at NUST.
Okay. And at
Ji.
which department?
At the Atta Rahman School of Applied Biosciences, ASAB.
Yes. Okay.
Ji.
It was nice to contact you. And
Ji, Dr. Saab,
hopefully
likewise.
we'll have some meeting at NUST as well, because I have some friends at the chemistry department.
Ji,
Have been
bilkul.
together during the student life, and even now we have some collaboration as well.
Great. No, I'm
University.
sure with the amount of work, mashallah, that you have done, I think it's really amazing to see this kind of work in Pakistan also, and especially in the field of hydrogels. Although we do see a lot of PIs working on hydrogel systems, but the commercial value of hydrogels is still yet to be explored in Pakistan. So this is one direction that definitely I'm taking for myself. So inshallah, let's see. So all the very best for your future endeavors, sir.
Okay, thank you very much, and I will be happy if you can share your email and we can contact some collaborative work. That I have some hydrogen systems, and I would like to explore some more applications related to biological or biomedical field.
Ji, inshallah, sir. I will be in touch, definitely.
Okay, thank you very much.
Thank you very much for your time. Thank you. So we will wind up our session lecture series for this session. Thank you so much for your time, and thank you very much to the audience who are listening on Facebook Live. Dr. Arzu, I think we'd end this session now.
Yes, Assalamu alaikum. I would also like to say thank you so much, sir, for a very interesting lecture. Although the topic is out of my research domain, yet for the first time, I was able to understand and learn about hydrogels in depth. I'm really intrigued and would also start looking for research loops I can fill theoretically using first principles calculations. Hope we can have more speakers like yourself on our platform and generally learn new research areas. Thank you so much for joining us. And thank you so much, Dr. Aisha, for hosting such nicely this lecture.
Thank you very much, Dr. Arzu.
Okay, thank you very much to all of you as well.
Okay, ji. Allah Hafiz.
Allah Hafiz.
Allah Hafiz.